talk here for a moment about the end of the semester here. So today is going to be the last day for content. We have still to do. We have today's content. Next class, we're going to do some in-class practice. We'll do a review day and then take the test, or maybe we'll smush the review day into the practice day. And then from there on, it's exam review guide and we're done, right? So that's it for the semester. Last time, while you guys were all doing your AP test, we worked on in class these 4 handouts right here. So you're not responsible for all of the 4 handouts. You can do every 4th problem. So let's say this set of students, you're going to start at problem 1 and then do every 4th problem on each sheet. So you start at 1 and then do 5 and then 10, etc. Yes, whatever. It's easy to count 4th problem, every 4 problems.
I started at 4 and then 8. I did 4, 8, 12, like I did like that.
Oh, whatever. That's fine. You guys start at 2. You guys start, Tesla start at 4. Deal?
Oh, wait, so we start 2?
Yeah, you guys start at 2.
2, 6.
Yeah, just count, every 4 problems or whatever. Right? So group 1 would start at 1, group 2 would start at 2, group 3 would start at 3, group 4 would start at 4, then group 1 would get 5.
Yeah, okay.
So it's like every 4 problem. If you did more than you're supposed to, or different, doesn't matter. I'm just trying to not make you do, like 100 problems. I'm trying to turn it into like 1 sheet worth of problems as opposed to 4 sheets. So it's just easy to just do a 4th of the problems and there's 4 sheets. It's like I'm doing 1 sheet and that's not a big deal. Everybody's okay? Okay. This is going to be like exactly the kinds of questions that'll be on the test or whatever. We'll do the same thing with series stuff. We're going to talk about series today. We'll do the same thing with some series sheets next class. That may count as the review day also. We'll just kind of play it by ear. And then test time and then exam review. So I have the study guides all printed up and ready to go. If you ask nicely, I'm going to you next week. If you want it early, I don't know how hectic the end of your semesters are looking, but very easy.
No, crazy.
Oh, very crazy. Yeah. So I didn't want to last minute it on you guys. So especially since you turn them in, you get to use it for the final, right? So you want to make sure you have enough time that you can spend some quality time on that. Everybody ready? Okay, Mark. Vamos. He's got to take a test. All right. So today, our last lesson for the semester, or at least new content anyways, we're going to be talking about a series. It's like the counterpart to a sequence. So a series, all we're talking about is just adding up the terms of a sequence. That's a series. So for example, if I have the sequence 2n minus 1, that's the terms 1, 3, 5, 7, 9, 11, etc. So the series then, Sn, I use S for series, would be like 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus ... Okay, what is really the difference between you look at a series and a sequence? plus signs instead of commas, right? That's your indicator as the difference. Everybody can see that? So if I want S3, that means I'm just going to be adding up the first 3 terms of my sequence. So like this is term 1, term 2, term 3. So I'm adding up 1, 3, and 5, which is just 9. S7 then would be 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13, which is 49, I think. Again, I just added those numbers up. What do you guys think? We okay with the notation as to what we're doing here? We call these guys partial sums. You may see that term being thrown around. So that's just adding up part of the sequence. It's a partial sum, right? So S3, S7, those are partial sums because they're just adding up the first 3 terms or the first 7 terms or the first n terms, as long as it's not infinite. Everybody's okay? Okay. So imagine if I asked you to write like S794. Would you want to write that out? No, right? We need to invent a notation to like make that a little bit more convenient. So what we call that notation is called sigma notation. So the sigma notation is what we use to represent a series. So the format for a sigma notation is we're going to have so if I have the series here, 1 plus 3 plus 5, we have the Greek letter sigma. That's this guy, that big E-looking thing. That stands for sum. We have the sequences explicit formula that we're going to be using to build the terms of our series. In this case, that was 2n minus 1. Notice I changed my variable from n to k so that I wasn't like abusing the n. This is like a different variable. So I just changed the name of it here to k. On the bottom of that sigma is the term number that we're going to start with. Usually that's going to be 1, but doesn't have to be, but usually. And then on top is going to be the last term that we add. In this case, that was 3 because there was 1, 2, 3 terms in our sequence that we added up. Does everybody feel okay with that? So our next example, what I want to do is I want to work on going from a sigma notation, expanding that out to a series, and then taking a series and compressing that down into a sigma notation. Okay, those would be the next 2 examples. All right, so when I look at this, what is the sequence that we're going to be adding up in this series? It's going to be 32 times 1/2 to the I minus 1. What term do we start adding at? 1. What term do we end our addition at? 5. So now I'm just going to go ahead and iterate this through, where I'm just plugging in the digits 1, 2, 3, 4, and 5 in for I. What do you guys think there? So far, so good? And now I just simplify this expression. And what do I get there? 62, it looks like. Do you guys feel okay with how I did that? Usually this way is quite easy, right? We're just plugging, we're using the formula and plugging in the number starting at the bottom and ending at the top into the variable in the in the explicit formula, just plus signs in between them, and then add up the numbers. No big deal. What tends to be a little trickier is when we want to go from the series into a sigma notation. So we're going to need three things out of this, right? We need to know the explicit formula, right? That's one. We need to know the first term we're starting with, number, and the term that we're ending with, term number, right? Now here it can be quite easy. If I just look, I'm adding 6 things up, right? So there's my first term number and my last term number. Everybody feel good on that? Now all I need is the explicit formula for the sequence. So if I look at this, it looks like it's arithmetic because I am adding 12 each time. And since I know the first term and the D, I can write my formula, my explicit formula for an arithmetic sequence quite easily, right? If I distribute the 12 through and combine some like terms, I got that. And so my sigma notation then would be that guy. So again, start, end, and explicit formula for the sequence that we're adding up. So basically just doing the same thing that we did last lesson, right? Tessa?
Where do you get the 6 from?
Because there are 6 things I was adding up. Now, Mr. Kulik, there's got to be like a catch, right? This gets trickier than this. Well, we can do something to make it a little bit meaner and add an extra step in here, but just marginally meaner. Okay, what if instead of having it, we'll do it on the next one. All right, so there are 2 special types of sequence or series that we want to talk about. Those are arithmetic series and geometric series. An arithmetic series just means we're adding up the terms of an arithmetic sequence. And a geometric series just means we're adding up terms of a geometric sequence. Everybody's okay with that idea? Hopefully that seems pretty obvious, I would hope. Now, the nice part is for each of these, we have a compact formula that lets us calculate any partial sum just based on the first term and the last term and the term number for arithmetic, and then the first term, the R, and the term number for geometric. So you don't actually have to enumerate each term out and add them together, which can be kind of a hassle. So let's practice using these formulas to compute these partial sums. Sound good? So first thing I want to do here is determine whether I'm looking at an arithmetic or geometric series. If I look at this one, it looks like we are subtracting 15 each time. So that tells me then I need to be, yes, sir. What do you need?
I'm trying to plug in an equation and it's just not working this fast.
Okay.
There's a flat line on the graph.
It's probably just your window.
No, but look.
Yeah. Sure. Why seem inappropriate to me?
It's just giving me a flat line.
So it says it's the year after 1960,
Oh,
so you want to have it look something like that.
yeah, that's my bad. Okay, thank you.
You're welcome.
Yeah, folks, starting.
Okay. So it's arithmetic, so we need this formula, right? We have the first term. We have the last term. What we don't have, though, given to us is the term number. Everybody's okay? So that is our goal. And then we have everything we need to plug into our formula. To get that term number, what we're going to do is we're going to write the explicit formula. Going to distribute the negative 15 through. And then I'm going to plug in that last term in my series and solve for n. I think that's 41. So that's what I need. So now if I go back to my formula, I have my first term. I have my last term. Oops. Come on, guys. Times that. Everybody feel okay? So what do we get when we type this all into the calculator? Negative 12,628. Notice that's a heck of a lot easier than enumerating out every term and then having to add them all up separately, right? You guys feel good on that? So the trickiest part is when I give you a series, but I don't show you every single term, I put that dot, dot, dot in the middle. All that means is you're going to have to solve for the n yourself, which means you have to write the explicit formula.
I didn't get that. Could you try again?
I hate you so much. It means you have to get the explicit formula, plug in the last term, and solve for n to get that final term number.
Why did you do the 41 over 2?
So the formula has times n over 2.
Oh, okay.
All right, let's look at this guy over here. What does this guy look like? Well, it definitely ain't arithmetic, right? How can you tell?
Because it eventually becomes a fraction.
Look at the signs.
It's how they
They're going from negative to positive to negative. Well, that can't be arithmetic possibly, right? So looks like it's probably going to be geometric. How am I going to find the ratio? I'll divide 96 by 64, and then 144 by 96, and then 216 by 144. And I get that same constant each time, right? So that tells me we're geometric. The first term is 64, and r is negative 3 over 2. You guys feel good? All right, so if I want that sum, I'm going to be using this formula, right? Because it's geometric. I have the first term. I have R. What I don't have, though, is N. What am I going to do? Same thing we just did. I'm going to write the explicit formula, plug the last term in, and solve for N. So there's my explicit formula. Everybody's okay with that? First term times R to the n minus 1. And we're going to plug in our last term. And we're going to solve for n. What should I do first to solve for n? Nope. The n is on the right-hand side. Why would I minus it? What operation is the 64 doing to the negative 3 over 2?
64.
There you go. Now, you can say divide by 64, and that's correct. I'm going to think about it as multiplying by 1 over 64, because the other side is a fraction. It's a little easier to handle it that way. Like I can do it in my head. So that gives us this. Everybody's okay? Then what? Where's that n located? In the exponent. How do I get something out of the exponent or cancel out the base of the exponential? What do I use to do that? A logarithm. Very good. Yes. Which logarithm should I choose? Log base.
3 over 2.
Well, what's the base of this exponential? It's negative 3 over 2. So ideally you'd want to use log base negative 3 over 2, right? Where the base of the log matches the base of our exponential. What's the problem though? Can't have a negative log base, and I can't take a log of a negative number. So that's going to be needing a little bit of adjustment, right? Well, here's the observation. Negative 2 to the third is negative 8. 2 to the third is
8.
positive 8. So if I just make both the base and the argument positive, the n stayed the same. I'm going to take advantage of that fact here. And to solve for n, I'm just going to drop the negative signs in those two locations. Everybody's okay there? That the answer to that equation for n will be the same as the other one, based on my argument about 2 to the third and negative 2 to the third. Everybody's good with that? Okay. So now we're ready to take log base 3 over 2 to both sides. So those guys cancel each other out, and we're left with n minus 1. Do you guys remember where the log base command is on your calculator?
Math.
Down at the bottom, it's just called log base. So I type that in, I get 7 to come out. So n is equal to 8. That's what I needed. So S8 should be the first term times 1 minus negative 3 over 2 to the 8th over 1 minus negative 3 over 2. Now I'll just type that into my calculator. and I get negative 1261 over 2. So you feel okay? So again, same process as before. The only thing that changes is the algebra involved to solve for n, because a geometric sequence is like a exponential equation, so we need a logarithm. A arithmetic sequence is like a linear equation, so we just need to add and subtract and divide. Max, what's up?
Okay, come on.
Sure. You guys feel okay with these ideas? Okay. Next up, what we want to talk about are infinite. I didn't mean sequences here, I meant series. Okay. So we say all infinite arithmetic series are divergent other than the trivial arithmetic series that's just zeros all the way through. Everybody's okay with that? What do we mean by divergent? Divergent means one of three things can happen. That the sum is infinity, the sum is negative infinity, or the sum cannot be determined. Like it's bouncing back and forth between some values. So for example, if I have the sequence that goes 1, negative 1, 1, negative 1, 1, negative 1, and that goes on forever. Imagine that, okay? If I add that up, well, that could have three answers depending on how many ones and negative ones I have. Those three answers could be, well, I could get negative 1, could get 0, or I could have positive 1, right? It's impossible to tell what the answer should be. That's indeterminate. Everybody's okay with that? Okay. So divergent just means that the sum is not a finite value that can be determined definitely. Now, for geometric series, or I should say infinite, if the absolute value of r is less than 1, then that infinite geometric series converges, and the sum we can calculate is the first term divided by 1 minus r. Otherwise, it diverges. So if that r value is, the absolute value of r is greater than or equal to 1, there's nothing to do with it. You just say it diverges and you're done. Everybody's okay? Yes, sir. Uh-huh. So if I go back and I look at if I had wanted to compute S infinity for this, what should my answer be? What's the R value here? Okay, is the absolute value of R greater than or equal to 1? Yes, right? What's the absolute value of 3 over 2? 1.5, right? So it's divergent, and you're done. There's nothing to do. That's all the work you need to show. You just need to check the R value. If you can do the sum, you plug it into the formula. If you can't, you're done. It's very nice because you don't need an N. Alex.
So like on our test, would it be us first solving like the actual problem and going back and seeing if it's divergent or not?
Or it could just ask it directly.
Okay.
Like here's an infinite, series. Is it divergent? If not, what is it, sum or whatever? Like. Is everybody okay? And then last thing I want to do is show you how to use the do these, use sigma notation on your calculator. So if you have a graphing calculator with you and you'd like to follow along, I invite you to do so. All right, so here we go. You guys ready? All right. What we're going to do is we're going to press the math button. We're going to scroll all the way down to the bottom till I see the summation command. That's command 0 on my machine. And now I can type it in exactly like it looks like on my sheet of paper. The only exception is, what's the variable letter on your calculator going to be used? X. So I'll just type it in exactly like this looks, except I'm going to use an X instead of an I. And then I press enter. And it's, boop, there's the answer. Oh, did I have, was it supposed to be a 7? It might have been. Yep, it was. Good job, guys. You did the right thing. I did the wrong thing. Well, that's because Mr. Kulik screwed it up. I made a mistake. There you go. How's that? Mm-hmm. Yeah, no big deal, right? Okay. Guess what, guys? That was it. Your assignment based on this is this, dagnabbit, this delta math. Let me just show you what that looks like. This delta math I'm going to show you is not due until the following Sunday. Go ahead. I just want to run through what it is you'll be doing and talk through a bit how to do it. Because there's one that has like a particular format that is worth at least showing you guys. So this is Delta Math 3. So the first type of questions are summations. How do I expect you to do this? Type that bad boy in your calculator and press enter. Type in the number you get. Everybody's okay? This one are all arithmetic series. I would encourage you to use the arithmetic series formula and then check it on the calculator using the summation button, but you should be able to do it with the formula. Okay? So you just be plugging 1 in for n, and then 81 in for n. That'll be your first term and your last term, and the n there is 81. Should be really easy. Same idea with our geometric series here. We might have to make a little adjustment because here we got to plug 2 in to get our first term. And the number of terms between 2 and 33, how many terms are there in between those? 32. Right, if between 1 and 6 you have 6 terms, between 2 and 6 you should have 5 terms. Same idea here, right? Everybody's okay? All right. Here you are given a series and asked to convert it back into sigma notation, just like we did in the homework or in the notes. Here is a geometric series. They're asking you to find the first 6 terms. So you have the first term, you have the n, you just have to figure out the r. Guys, look, it's 1/5. And like, that's all she wrote. You just plug it into the formula and press enter. Here we made it a little bit harder and hid the value for n. So you have to write the explicit formula first and then solve for n. But then you're just plugging into this formula still. Here we've mixed them together. There's arithmetic and geometric mixed together. You have to figure it out first. which one it is and then use the appropriate formula. And then the last one are these infinite geometric series. So if I look at this, we want to ask ourselves first, is this a geometric series? Looks like I'm multiplying by 3 over 2 each time. So we say is. The common ratio here is 3 over 2. We'd say this series diverges because its R value is greater than or equal to 1 or -1. So this one has like a bunch of drop boxes to fill in. That's the one that where it's like kind of confusing what to do with this. What do you guys say? Okay, so this is the third and final Delta Math. Next class we'll do some series practice worksheets and put together our half sheet and all that jazz. Okay?
I just can't put the variables.